Tonight, we're going to explore one of the most hostile environments life has ever faced in the story of human ambition, Mars. For decades, we've imagined it as humanity's next home, the place where we'll build the first cities beyond Earth, a second world where our species might one day survive if something happens to the first. But there's a problem. Mars doesn't just make life difficult, it makes life almost impossible. Step onto its surface without protection, and you'd lose consciousness in seconds. Minutes later, you'd be dead. The air is almost non-existent. The temperatures can plunge far below anything naturally experienced on Earth. The radiation never truly stops. Even the ground beneath your feet is hostile to human biology. And yet, despite all of that, Mars often looks strangely familiar. That's part of what makes it so deceptive. By the end of tonight, you'll understand why Mars is not simply a frontier waiting to be settled, how its gravity, radiation, toxic soil, and isolation each attack a different part of what keeps us alive, and what it really means to send human beings to a planet where every single day is a battle against the environment itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The images are the first thing that gets you. Perseverance, rolling across a rust-colored plain, its tracks pressed into ground that looks almost familiar. Curiosity photographing rock formations that could pass for a desert canyon in the American Southwest. Ancient riverbeds carved into the Martian surface, their shapes identical to channels cut by the water on Earth. Ice deposits near the poles, bright and real. Looking at those images, something in you relaxes. Mars looks like a place you could walk through. Barren, yes. Cold, certainly. But a place. That feeling is wrong. Mars is roughly half the size of Earth. Its surface gravity is about 38% of what you feel standing here. That means a person who weighs 180 pounds on Earth would weigh roughly 68 pounds on Mars. Lighter, yes. But gravity is not just about weight. It shapes how fluids move through the body, how bones load and unload, how the heart distributes blood. 38% gravity is not a gentler version of Earth gravity. It is a different mechanical environment your biology has never encountered and was never designed for. Then there is the atmosphere. On Earth, atmospheric pressure holds your blood in its liquid state. It keeps your tissues in equilibrium. It is the invisible pressure that makes you possible. On Mars, that pressure drops to about 0.6% of Earth's, 0.6%. To put that in physical terms, the air at roughly 30 kilometers above Earth's surface, 3 times higher than a commercial jet flies, has roughly equivalent pressure. There is almost nothing there. And on Mars, almost nothing is everywhere, right at the surface. What happens to an unprotected human in that near vacuum is not complicated. It is fast. Without pressure to keep your blood stable, it begins to boil. Not from heat, from the absence of containment. The dissolved gases in your blood come out of solution, the same way a carbonated drink fizzes when you open it. Your body swells. You lose consciousness in about 15 seconds. Death follows in roughly 90 seconds. There is no dramatic struggle. The planet simply does not permit you to exist at its surface without a layer of technology between your skin and the air. But here's where it gets strange. That technology, as good as we can make it, does not make Mars safe. It makes Mars survivable, temporarily, in narrow corridors of engineered protection. The suit keeps the pressure in, the habitat keeps the cold out, and Mars keeps working. Because Mars has had roughly 4 billion years to develop mechanisms that destroy biology at the surface. Every process that stripped away its atmosphere, every bombardment that churned its soil, every ultraviolet ray that now reaches its surface unfiltered, those processes have been running for an unimaginably long time. The danger is not accidental, it is baked into the planet's chemistry at a level we are only beginning to measure. In 2008, NASA's Phoenix lander touched down near the Martian North Pole and began analyzing the soil beneath it. The lander was designed to look for signs of habitability. It found something unexpected: perchlorates. Perchlorates are chlorine-oxygen compounds. On Earth, they are most familiar as components of rocket fuel, fireworks, and explosives. They are energetically reactive, and in 2008, Phoenix detected them not as a trace contaminant, but as a consistent presence throughout the Martian soil, at concentrations of about 0.5% across the dirt a colonist would stand on, work in, and breathe near every single day. 0.5% sounds negligible. That is the setup. Here is the reveal. The European Space Agency has established a safety limit for perchlorate exposure of 0.7 milligrams per kilogram of body weight per day. A 2025 study published in the journal GeoHealth found that inhaling just a few milligrams of Martian dust would push a person past that daily safe limit. Not past it after weeks of accumulation. Past it in a single exposure. Not a trace chemical to monitor over time. A daily threshold you breach by breathing the dust. And the dust on Mars moves. Storms carry it across continents. It settles on every surface, infiltrates seals, coats instruments. A habitat is not airtight in the way we might imagine. Airlocks cycle. Equipment comes inside. Boots tracked across a floor. Every entry is a potential vector. The perchlorates are not sitting still waiting to be avoided. They are ambient. The thyroid gland processes iodine. Perchlorates interfere with that process. They compete with iodine for uptake, disrupting the hormones the thyroid produces. Those hormones regulate metabolism, cognition, development. In children, the damage can be severe and permanent. In adults, the effects accumulate. Disrupted hormone production affects energy, mood, immune response, reproductive function. The body does not adapt to this. There is no version of long-term perchlorate exposure that the human endocrine system learns to accommodate, and nobody has studied what years of it does. That is not a rhetorical point. It is a genuine gap in the science, because no human being has ever lived through it. Earth-based safety limits were developed from relatively short-term studies of isolated industrial exposures. A colonist on Mars would be inhaling perchlorates, potentially eating them through crops grown in Martian soil and absorbing them through every imperfect seal for years. Maybe a decade, maybe longer. What that timeline does to the thyroid, to cognition, to the hormonal architecture of the body, we genuinely do not know. What we do know is that the soil underfoot is not neutral ground. It is not simply dirt waiting to be planted. Every step a suited human takes on Mars is a step on a surface that, given any pathway into the body, begins working against it. And perchlorates are only the beginning. So start with the dust itself. Not what it carries, what it is. Martian dust particles are roughly 3 micrometers in diameter. That is about 4% of the width of a human hair. Put another way, the particles are so fine that the eye cannot resolve them individually. They are not like the dust on a bookshelf. They are not like the grit on a desert road. They are closer in scale to the particles released by industrial grinding, the kind that occupational health agencies have spent decades trying to keep workers from breathing. And on Mars, the air is full of them. Particle size determines where in the body a particle lands. Large particles, the kind you can see, get caught in the nose and throat. Smaller particles make it into the upper lung. A particle at 3 micrometers, something near the lower limit of what the respiratory system can even intercept, penetrates deep, past the airways, into the small sacs of the lung, the alveoli, where oxygen crosses into the blood. At that depth, the body has few defenses. What gets in tends to stay in. We have seen something like this before, not on Mars, but on the Moon. The Apollo astronauts brought lunar dust back with them, on their suits, on their gloves, inside the lunar module. Several crews reported reactions that resembled hay fever. Watering eyes, scratchy throats, a persistent irritation that did not resolve quickly. Apollo 17 geologist Harrison Schmitt had a particularly severe reaction. His symptoms were acute enough that they prompted NASA to begin formal studies of lunar dust after the program ended. The Moon's dust, geologically young and never worn smooth by water or wind, is jagged at the microscopic level. It tears rather than slides. And it caused measurable harm after exposures measured in days. Martian dust is thought to be far more dangerous. Not roughly more dangerous, far more. And the exposure horizon for a Mars colonist is not days. It is years. In February 2025, a study led by Justin Wang with researchers from USC, the University of Colorado Boulder, and NASA Johnson Space Center described what they called a laundry list of dangerous compounds found in Martian dust. The word laundry list is worth pausing on. It is not dramatic framing for effect. It reflects the actual breadth of the problem. This dust does not have one hazardous component. It has several, each working through a different biological mechanism. The first is silica, Silica is one of the most common minerals in Martian soil, and it causes silicosis. That is a well-documented disease. Coal miners, quarry workers, construction workers who cut concrete and sandstone have developed it for more than a century. Silica particles lodge in the lung tissue and trigger an inflammatory response the body cannot resolve. Over years, the inflammation creates scar tissue. The scars are permanent. Breathing capacity drops. The damage is progressive and irreversible. There is no treatment that restores scarred lung tissue, and a significant portion of the dust a Mars colonist would breathe every day contains silica, not as a trace component, as a substantial fraction. But silica is not even the most behaviorally unusual component. The iron oxides are. Iron oxides are what make Mars red. That distinctive color, visible from Earth, comes from iron that has oxidized over billions of years of geological activity. Those same iron oxides are present throughout the dust, and they carry a property that silica does not. They make the dust magnetic, electrostatic. The particles do not simply settle, they cling. They stick to suit fabric, to equipment surfaces, to habitat walls. They resist brushing. A colonist who walks in from a suited excursion will use airlock brushes and compressed air to remove dust from the exterior of the suit. Most of it comes off. A fraction does not. Some always gets through. Over weeks, that fraction accumulates. Over months, it becomes a measurable presence inside the habitat. Over years, the colonists are living in a space where every surface carries a residue of Martian dust, and they are inhaling small amounts of it with every breath, continuously, with no way to fully stop it. The electrostatic behavior of the dust defeats even careful cleaning protocols. This is not a failure of engineering. It is a consequence of the dust's chemistry. The Wang 2025 study also flagged gypsum, which is calcium sulfate, as a component. Gypsum causes respiratory irritation with prolonged exposure. It is not the most alarming compound on the list, but it adds to the cumulative load. Then there are the trace metals: arsenic, chromium, beryllium, all present in Martian dust at low concentrations. Low is a relative term. These are not compounds the human body handles without consequence at any sustained level of exposure. On Earth, industrial exposure limits for these substances exist because chronic inhalation causes serious harm, from lung cancer to systemic toxicity to conditions that damage organs well beyond the respiratory system. In the Martian case, concentrations are low enough that acute poisoning is not the concern. Chronic exposure over years is, and here the science hits the same wall it hit with perchlorates. No human being has lived through sustained low-level exposure to these specific combinations in this specific environment. The long-term effects are genuinely unstudied, not poorly understood, unstudied. There is no dataset. There are no long-term human subjects because no long-term human subjects have existed. What we can say is this: dust that carries silica damages the lungs mechanically and irreversibly. Dust that is magnetic and electrostatic infiltrates every space the colonist inhabits. Dust that carries arsenic and chromium and beryllium introduces compounds whose chronic effects at low doses, over years, in low-gravity, low-pressure conditions, we cannot predict. Each of those facts holds independently. Together they describe something the word nuisance cannot touch. This is not a background inconvenience. It is a permanent, ambient occupational hazard, present on every shift, on every suited excursion, inside every airlock cycle, inside the habitat itself. The colonist does not encounter it occasionally. They live inside it. And the dust does not work alone. Something else is reaching them. Something they cannot see, cannot feel, cannot filter out through any seal or scrubbing system. While the dust works on the airways, the Martian environment is doing something quieter and more pervasive to every cell in the colonist's body. Earth has a magnetic field. It wraps around the planet like an invisible shell, deflecting charged particles streaming in from the sun and from deep space. Most of those particles never reach the surface. They are turned aside, redirected, absorbed by the magnetosphere, and then by the atmosphere above. A person living on Earth is shielded by this system every moment of their life, and they never think about it. Mars lost that shield about 4 billion years ago. The core cooled. The dynamo that generated the global magnetic field went quiet, and the planet has been exposed ever since. What that means for anyone on the surface is not complicated to state. It is hard to absorb. Something else is happening. With no magnetic field and an atmosphere only a fraction of Earth's thickness, Mars receives two distinct streams of radiation continuously. The first comes from the Sun. Solar flares and coronal mass ejections release enormous bursts of high-energy particles. On Earth, those particles are largely deflected before they can reach anyone. On Mars, they arrive at the surface. The second stream is older and stranger. Galactic cosmic radiation is a constant background flux of particles, accelerated near the speed of light by supernovae and the other violent events far out in the galaxy. These particles have been traveling for thousands or millions of years. They do not stop at Mars. There is nothing to stop them. NASA's Curiosity rover has been measuring radiation on the Martian surface since 2012. Not from orbit, from the ground, at the level where a person would actually live and work. The numbers it has returned are specific, and they are not ambiguous. The daily surface dose is approximately 67 millisieverts. A millisievert is a standard unit for measuring radiation absorbed by biological tissue, weighted for the type of damage it causes. To give that number scale, the general public in most countries is considered safe at 1 millisievert per year. 1. That is the threshold below which regulatory bodies conclude radiation poses no meaningful threat to long-term health. Nuclear power plant workers, people whose profession involves regular radiation exposure under careful monitoring, are permitted up to 50 millisieverts per year. On Mars, a colonist receives 67 millisieverts in a single day. Not in a year, not in a month, in a day. A Martian year runs 687 Earth days. Over the course of one Martian year on the surface, the accumulated dose reaches approximately 230 millisieverts. That is more than 200 times the annual limit considered safe for the general public. It is more than 4 times the annual limit for nuclear workers. And it does not stop. The next Martian year brings another 230 millisieverts. The year after that, another. There is no rotation, no recovery period, no safe posting somewhere else on the planet. Every location on the Martian surface receives the same unshielded exposure. Wait, this is not extra radiation in the way an occasional X-ray adds a small dose on top of a safe baseline. This is a sustained, unrelenting biological load that begins the moment a colonist steps onto the surface and does not diminish. The biological consequences of that load are not speculative. Ionizing radiation damages DNA directly. High-energy particles pass through tissue and break chemical bonds, cutting through the double helix in ways the cell's repair mechanisms were not designed to handle at this frequency. The result is elevated cancer risk. Not slightly elevated, exponentially elevated, growing with cumulative dose over the years of emission. Beyond cancer, radiation at these levels affects the central nervous system. Studies on astronauts aboard the International Space Station, who receive far lower doses than a Mars surface colonist would, have shown measurable changes in brain structure and cognitive function. At 230 millisieverts per Martian year, the neurological effects would be more severe and would compound over time. Cardiovascular tissue is also vulnerable. Chronic radiation exposure has been linked to accelerated development of heart disease, an additional load on a body already managing the cardiovascular strain of low gravity. These are 4 distinct biological systems under pressure simultaneously. The genome, the brain, the heart, the lungs. And on the lungs, the radiation does something specific that circles back to what the dust has already begun. Radiation increases susceptibility to pulmonary fibrosis. Pulmonary fibrosis is the progressive scarring and stiffening of lung tissue, a process in which healthy, flexible tissue is replaced by rigid scar tissue that cannot perform gas exchange. The lungs gradually lose function, the condition is irreversible. Radiation exposure primes the lung for this process by damaging the cells that line the alveoli and disrupting the tissue repair mechanisms that would normally contain localized inflammation. Mars also provides, continuously and unavoidably, the fine silica-laden dust that initiates the same inflammatory cascade through a different pathway. The colonist does not face these two hazards in sequence. They face them simultaneously, from the first day. The radiation sensitizes the lung tissue. The dust exploits that sensitization. 2 processes, arriving from opposite directions, converging on the same organ, each making the other more destructive than it would be alone. Not 2 separate problems, 1 feedback loop. Something else sits underneath all of this, quiet and unresolved. When we say Mars lost its magnetic field 4 billion years ago, we are describing a planetary death that left its mark on everything that followed. Why that happened, how a world with liquid water and a thickening atmosphere became what Mars is today, is a story the numbers do not fully tell. It is one of the deeper questions the planet holds. It does not need an answer here, but it is worth sitting with for a moment. The thing protecting a colonist's DNA from cosmic radiation is a function of planetary geology, of deep time processes that unfolded long before any human being existed. Mars made a different set of decisions 4 billion years ago. The colonist lives with the consequences, and radiation is not the last of them. The storms do not arrive without warning. That is the strange part. On Mars, a dust storm announces itself days in advance, a regional disturbance visible from orbit, growing at the edges, pulling more dust into itself, feeding on the atmosphere it disrupts. You can watch it spread. What you cannot do is stop it. And over the course of weeks, a storm that began as a weather event in one hemisphere can become something the word weather no longer fits. It becomes a condition. The whole sky goes dark. The dust does not settle for months. On Earth, no storm works this way. No weather system on this planet grows until it covers the entire surface. The largest dust storms on Earth, the ones that cross continents, are still regional events measured in thousands of miles. On Mars, the atmosphere is thin enough, and the dust fine enough that once a storm reaches a certain scale, it feeds itself, absorbing heat, lifting more particles, expanding outward across plains and craters and polar regions until the planet wears the storm like a second skin. The storm is not happening somewhere on Mars. It is Mars, for months at a time. In 2018, that happened. A dust storm grew through May and June of that year. It became global. The sky above Mars darkened until the surface received roughly 1% of its normal sunlight. That figure sounds like a dramatic reduction. It was a near total blackout. NASA's Opportunity rover had been operating on the Martian surface for nearly 15 years by then. It had outlasted every prediction for its survival. It had crossed dozens of miles of terrain, transmitted hundreds of thousands of images, and survived 7 Martian winters. It was solar-powered. The storm covered the sky and cut off its sunlight. Opportunity sent its last communication in June 2018. Engineers waited through the storm. They sent recovery signals for months after the sky cleared. The rover never responded. Nearly 15 years of operation. A single storm. Weeks to silence what a decade and a half had built. That is not a framing. That is the record. For humans on Mars, the 2018 storm is a template for what a global event means in practical terms. A base that depends on solar panels for primary power loses that power when the sky goes dark. Not a reduction in efficiency. Not a partial shortfall that batteries compensate for over a day. A weeks-long, potentially months-long loss of the primary energy source. A base with nuclear backup power survives that. A base without it does not. The margin between those two outcomes is not engineering detail, it is the survival question. But here is where it gets more complicated than power alone. During a global storm, EVAs become effectively impossible. The dust reduces visibility. The particles accumulate on suits and equipment faster than any maintenance protocol can address. The mechanical systems that keep suits pressurized and sealed face sustained stress from particles that behave electrostatically, that cling, that find their way into joints and seals and valves. Going outside during a global storm is not a calculated risk. It is a prohibition. That confinement compounds everything else. The crew cannot go outside for maintenance. They cannot check equipment. They cannot repair solar panels, inspect the habitat exterior, or perform any of the physical tasks that keep a surface base operational. If something fails during the storm, the crew works with what they have inside. If a component needs hands-on repair on the exterior of the habitat, it waits. Weeks, months, whatever the storm demands. Supplies move in one direction during that time. Down. Air recycling systems run continuously under a load they were not optimized for. Food reserves shrink at a pace determined by calendar days, not by mission milestones. The crew cannot accelerate any timeline. They wait. The psychological weight of that confinement is not easily translated into technical language. Human beings in confined spaces, under sustained pressure without physical access to the outside, with no clear end date, with tasks waiting that cannot be done, show measurable psychological deterioration. The duration is the variable that makes Mars different from any analog environment on Earth. Antarctic winter stations confine crews, but the confinement has a known endpoint and the sky outside changes. On Mars, during a global storm, the sky shows nothing. Weeks of that becomes months of that. The crew is sealed inside a habitat waiting for a planetary weather event to end on its own schedule. And the storms do not announce their end date either. They dissipate gradually, settling over days and weeks as dust falls back to the surface. The light returns slowly. For a crew that has been confined, the return of usable solar power is not a sharp line. It is a slow recovery, measured in climbing numbers on energy monitors. Even outside the storms, the dust is always working. Under ordinary Martian conditions, dust accumulates on solar panels at a rate that reduces their efficiency by roughly 15% in a single month. Not through any dramatic event. Simply through the ambient atmosphere. Particles settle. They are too fine and too electrostatically charged to blow away. They cannot be removed by shaking or mechanical vibration. They have to be physically wiped clean, by hand, on the outside surface of the panel, in a suit, in the cold, in the thin air. The planet imposes that maintenance task on every day that solar power is part of the energy plan. The 2018 storm is the acute version of that ambient process. The storm that silenced opportunity in weeks was the same Martian dust that operates at 15% efficiency loss per month on ordinary days. The same particles, the same physics, operating at different scales. One is chronic, one is catastrophic. Both require a response the environment makes difficult, and the environment offers no concession between them. Mars does not separate its hazards into categories. The dust that accumulates on a panel on a clear afternoon is the same dust that fills the sky during a global storm. The weather system that might confine a crew for months is built from the same atmosphere they live inside every day. Everything connects. And the storms are not the last thing that connects. All of that connects to something smaller. Something personal. Something measured not in planetary scale, but in the length of a single day. Step inside one morning. Not during a global storm. Not during a crisis. An ordinary morning on a day when the hazards are simply ambient. When the dust is accumulating and the radiation is arriving, and the systems are functioning as designed. This is what life on Mars looks like when everything is going well. The sleeping quarters are a pod barely larger than a closet. That is not an approximation. Every cubic meter of pressurized volume costs mass and money to deliver from Earth. So the habitat is built to the smallest dimensions that allow a person to function. The interior lighting is programmed to cycle through an artificial day-night rhythm, mimicking the pattern of Earth, because circadian disruption compounds quickly into sleep loss, cognitive impairment, and health decline. Light is not a luxury on Mars. Light is a medical intervention. The first act of the morning is not breakfast. It is checking the radiation monitor. The instrument logs overnight solar events, and most mornings it reads within the normal range of high. Not safe, normal. But a few weeks ago, a coronal mass ejection reached Mars. A coronal mass ejection is a sudden eruption from the sun's surface, releasing a wave of high-energy charged particles across the solar system. When the readings spiked, the crew moved into the storm shelter, a compact pod surrounded by water tanks whose density absorbs a fraction of the incoming radiation. They stayed there for 14 hours. They were waiting for the readings to fall from what one instrument described as immediately lethal to the lower threshold of merely dangerous. 14 hours in a room, smaller than a closet within the closet they already live in. Then it passed, and they came back out and went on with the day. Breakfast is protein bars. The habitat's biological lab produces them from algae cultures and cultured proteins, and they are nutritionally adequate. They taste like cardboard. Fresh vegetables grown in cleaned regolith are available, sometimes on days that count as special occasions, because cleaning Martian soil well enough to grow food safely consumes quantities of water the habitat cannot spare routinely. All water on Mars is recycled. Drinking water is recovered from prior sweat and urine, processed through filtration systems, and returned to the tap. The systems that accomplish this are engineering achievements. They are also simply how water works on Mars, and thinking about them too long serves no practical purpose. EVA preparation begins after breakfast. EVA stands for extravehicular activity, meaning any operation outside the pressurized habitat. Suiting up takes approximately 30 minutes. Each seal on the suit is checked. Each connection point is verified. And then a second person checks all of it again. The buddy system is not optional and not abbreviated. One person examines every seal on the other person's suit before either of them steps into the airlock. A single seal failure does not mean a difficult day. It means death. The suit is the atmosphere. Without the suit, the atmosphere of Mars kills in under 2 minutes. When the outer airlock door opens, the sky above is butterscotch. Not blue, butterscotch. A dusty amber orange that fills the horizon in every direction. On Earth, the sky is blue because the nitrogen and oxygen molecules in the atmosphere scatter shorter wavelengths of light, and blue sits at the short end of the visible spectrum. On Mars, the suspended dust particles scatter longer wavelengths instead, and the orange and yellow frequencies dominate. The same physics, the opposite result. It is one of the genuinely strange beauties of the place, and there is a moment at every EVA where a person looks up and registers it. Then, the work begins. Movement in 38% of Earth's gravity sounds intuitively like an advantage. It is not playful. It is not the bounding footage from Apollo on the moon. A fall in a pressurized suit on the Martian surface is not a minor inconvenience. A fall can damage a seal. A damaged seal compromises the pressure boundary between the inside of the suit and the atmosphere outside it, which means a fall can kill. So movement is deliberate, measured, and slow. Not because the gravity demands it, because the suit requires it, and the suit is the only thing standing between a functioning human body and the environment described in the previous 4 hours of this conversation. The task today is cleaning the solar panels. Electrostatic Martian dust has settled across their surfaces and reduced their output. The panels have to be physically wiped, each one with a gloved hand, using a soft tool that will not scratch the surface. On Earth, a competent technician with a proper kit could clean a comparable array in 20 minutes. On Mars, the same task takes 2 hours. The suit limits range of motion. The thick gloves eliminate fine motor control. Every movement that would be casual in a t-shirt and sneakers requires concentration and effort in 30 kilograms of pressurized equipment. The task cannot be rushed. Every extra minute outside adds radiation exposure. It adds micrometeorite risk, because particles too small to track on radar pass through the thin atmosphere without slowing significantly. It adds the possibility of a mechanical failure in the suit itself. 2 hours of careful, methodical wiping, because 15% of the panel's monthly efficiency disappears if it is not done. Not a job that can wait. Not a task that can be delegated to a machine. A recurring physical requirement of staying alive. Return to the habitat begins with the outer airlock. 15 minutes in the chamber, using brushes and compressed air to remove as much surface dust as possible before the inner door opens. The protocol works, partially. Some dust gets through. The same electrostatic iron oxide particles that cling to the suit exterior find their way inside anyway, in quantities too small to see and too consistent to prevent. Week by week, month by month, the interior of the habitat accumulates what the airlock was designed to exclude. This is the chronic exposure argument at its most tangible, not a contamination event, a gradual accumulation that does not stop. Later that afternoon, one crew member has a persistent cough. It has been present for several days. The question it raises has no immediate answer. Irritation from the dust levels inside the habitat is plausible. The beginning of something more serious is also plausible. There is no hospital on Mars. There is a medical bay with diagnostic equipment, and a trained medic, and a supply of medications and surgical tools for basic procedures. If the cough resolves into an ordinary respiratory irritation, the medical bay is sufficient. If it resolves into something requiring complex pulmonary surgery, or oncological treatment, or any intervention beyond what the bay can provide, the person with the cough will die on Mars, not because care is unavailable in theory, because the nearest hospital is tens of millions of miles away, and the transit window to reach it opens only every 26 months, and the body does not always wait for windows. Isolation is total. That word carries weight. Total means no evacuation, no escalation, no second opinion from a specialist on another continent. Total means the medical resources present in the habitat are the ceiling of what is possible. And people will still go. Humans have always moved toward the unknown, even when the unknown is dangerous and the cost is real. The scientific questions Mars can answer are profound. The philosophical payload of setting human eyes on another world is something that resists easy dismissal. None of that is dishonest. None of that is wrong. But the morning described here is what that decision means in practice. The radiation monitor at dawn, the cardboard bar for breakfast, the 30 minutes of seal checks before stepping outside, the 2 hours of deliberate, careful wiping in a suit that cannot be allowed to fall, the 15 minutes in the airlock that does not quite finish the job, the cough at the end of the day that may be nothing and may not be. People should go with open eyes. And the open eyes account does not end with the hazards already named. What makes Mars worth all of that? The question deserves a real answer. Not a philosophical abstraction about the human spirit. A concrete answer about what Mars actually holds and why scientists believe it may be among the most scientifically valuable places in the solar system. Start with the ground itself. Earth's surface is not a museum. It is a construction site that never closes. Plate tectonics constantly recycle the crust, pulling old rock down into the mantle and pushing new rock up from below. Erosion wears away mountains. Rain dissolves minerals. Biology breaks down stone and rebuilds it. Most of Earth's ancient surface is simply gone. The oldest exposed rock on Earth is roughly 4 billion years old, and finding it requires traveling to geologically quiet corners of Canada and Greenland, places that have somehow escaped the constant churn. Mars has no plate tectonics. Its crust has not moved in billions of years. The surface sitting under that thin veil of dust today is largely the same surface that was there when the solar system was still young. Walking on Mars would mean walking on terrain from the birth of the planets. Not a reconstruction. Not a fossil of a surface. The actual surface. Preserved and waiting. That is not a metaphor. That is what a geologist would find when they kneel down and press their gloved hand into Martian soil that has not been touched by tectonics, erosion, or biology in 4 billion years. The scale of what that preservation produced is difficult to hold in the mind. Consider Olympus Mons. It is the largest volcano in the solar system. It rises roughly 21 kilometers above the surrounding plains. Mount Everest, the tallest mountain on Earth, rises about 8.8 kilometers above sea level. Olympus Mons is approximately 2.5 times that height. Its base spans roughly 374,000 kilometers in circumference. A structure of that size could not exist on Earth. On Earth, the hot spot that feeds a volcano sits fixed in the mantle, while the plate above it slowly drifts. The magma punches through at one point, builds an island or a mountain, and then the plate carries that structure away before more magma arrives. That is why Hawaii is a chain of islands rather than a single colossal peak. Each island formed over the same hotspot and was then dragged away. On Mars, the crust never moved. The hotspot kept feeding the same point for hundreds of millions of years, and the magma kept piling up. The result was Olympus Mons, a structure that should not be possible by the rules governing every other rocky planet we know. Then, there is Valles Marineris. On Earth, it would be called the grandest canyon in the solar system, and on Mars it earns that name without competition. It stretches roughly 4,000 kilometers in length. Placed on Earth, it would span the continental United States from coast to coast. It reaches roughly 200 kilometers across at its widest point, and drops up to 7 kilometers deep. The Grand Canyon could fit inside Valles Marineris many times over without touching the walls. But the picture does not hold. Valles Marineris is not simply a canyon carved by water or wind. It is a rift system. The crust itself was pulled apart. Something split the Martian crust from the inside, and the internal forces that caused that splitting are not fully understood. The canyon is there, enormous and undeniable. The mechanism that made it remains an open question. These geological features alone would justify sending humans to Mars, but they are not the primary reason scientists argue the planet is scientifically irreplaceable. The primary reason is water. Mars once had it. The surface of Mars carries the shapes of ancient riverbeds, lake basins, and shorelines. The atmosphere was once thick enough to sustain liquid water on the surface. And wherever liquid water exists on Earth, life follows. This is not a hopeful assumption. It is an empirical observation. Hot springs in Yellowstone carry microbial life in water near boiling. Deep sea vents on the ocean floor, in total darkness under crushing pressure, sustain entire ecosystems built on chemistry rather than sunlight. Lakes buried under kilometers of Antarctic ice, isolated for millions of years, still harbor living organisms. The pattern holds: liquid water, life. Everywhere on Earth that the first is present, the second appears. Mars had liquid water. The question is, what happened to the life that may have emerged there when conditions allowed it? The surface became cold and thin and hostile. But the question is not only whether life existed on Mars. The question is whether any of it survived. Underground aquifers may still hold liquid water today, warmed by geothermal heat and insulated from the surface by kilometers of rock. Ice deposits exist in the subsurface and at the poles. If life retreated into those spaces as the surface became uninhabitable, some form of microbial life could still be present on Mars right now. Not as a certainty, as a genuine possibility that planetary scientists take seriously. Perseverance, the rover currently operating on Mars, is collecting rock and sediment samples from Jezero Crater, an ancient lakebed that once held standing water for potentially millions of years. Those samples are being sealed and cached on the Martian surface for a future sample return mission that would bring them back to Earth for analysis. The analysis could reveal organic molecules, chemical signatures of biological processes, possibly fossilized microbes preserved in ancient sediment. If any of those results came back positive, it would be one of the most significant findings in human history. Not significant in a contextual or academic sense. Significant in the sense that it would prove life is not a fluke, that it arises independently wherever conditions allow, that the universe is, at minimum, a place where life can happen more than once. That is what Mars holds, and that is also what makes the ethics of colonization complicated in a way that goes beyond engineering. If Martian life exists, even microbial life in a subsurface aquifer, do humans have the right to send colonists there and risk contaminating a biosphere that evolved independently over billions of years? Planetary protection protocols require spacecraft to be sterilized before launch to prevent forward contamination. Earth organisms, carried accidentally on a spacecraft, could potentially survive in Martian environments and corrupt the very biology scientists are trying to study. The returned Martian samples, currently planned, will be held at biosafety level 4. That is the same containment level used for Ebola. Not as a precaution against a known threat, as a precaution against an unknown one. The concern runs in both directions. If Martian microbes were returned to Earth, and if those microbes were biochemically compatible enough to interact with Earth organisms, but different enough from anything Earth life has encountered to evade immune defenses, the consequences could be severe. Scientists treat this not as science fiction, but as a category of risk that requires genuine containment planning. The scenarios explored in works like The Andromeda Strain and War of the Worlds were imaginative. The underlying concern is not. Colonization does not simplify this dilemma. It deepens it. A permanent human presence on Mars means a permanent introduction of Earth biology into the Martian environment. Thousands of organisms arriving and surviving and changing the chemistry of every surface they touch. If life exists on Mars, colonization is an act with consequences that cannot be undone. The settlers would not simply be occupying an empty world. They would be entering a living one. That is the weight the Open Eyes account carries alongside the suit seals and the radiation monitors and the compressed air canisters. Mars may be one of the most scientifically irreplaceable places in the solar system, and that irreplaceability is itself part of what makes going there a decision of a different kind than any frontier humanity has crossed before. The geology, the life question, the contamination risk in both directions. Those are the terms of the choice, and they are not the last of them. All of that weight belongs somewhere. The philosophy, the contamination risk, the question of whether Mars is empty or alive. But none of those considerations change the one thing that everything else depends on: water. Not symbolically, literally. Water is what a colonist drinks, what the crops need to grow, and, as it turns out, one of the best materials available for blocking the radiation that would otherwise accumulate in the body hour by hour, day by day. Pull on that single thread, and most of the colony's structural logic unravels from it. Mars is not a dry world. That distinction matters. The polar ice caps hold vast quantities of water ice, enough that if all of it melted, it would spread a shallow ocean across the entire surface. Orbiting radar systems have detected subsurface ice deposits extending well into the higher latitudes, buried beneath the regolith at depths that vary with location and season. There is also evidence of briny water seeping down crater walls during Martian summers, dark streaks that appear and fade in patterns that suggest liquid movement. Whether those seeps are actually liquid water is still debated. The chemistry involved including salts that dramatically lower the freezing point, could explain the appearance without requiring flowing water in any conventional sense. Scientists have not resolved this. What they have confirmed is that water exists on Mars in substantial quantity, locked in forms that require significant effort to reach. The polar ice is the largest reserve, but the polar regions present problems that compound each other. Polar winter temperatures fall below minus 125 degrees Celsius. Extended darkness accompanies that cold, which means solar power drops to near zero precisely when the machinery would be working hardest against the most extreme conditions. The ice itself is not pure. It is mixed with frozen carbon dioxide, what most people call dry ice, and separating water from carbon dioxide requires careful, controlled heating. Too fast, and the water sublimates before it can be collected. Too slow, and the energy cost rises without bound. Running heavy extraction equipment in those temperatures, in that darkness, with minimal maintenance capacity and no spare parts arriving for years, is not an engineering challenge at the edge of capability. It is several engineering challenges stacked on top of each other. Subsurface ice at lower latitudes is more accessible in some respects. Closer to the equator, temperatures are warmer and solar power is steadier. But the ground itself introduces a different problem. Martian regolith varies considerably in its physical properties. In some locations, it behaves as expected, loose and granular. In others, where cementing processes have bound the particles over geological time, it is almost concrete-like. Drills encounter it. Scoops deflect off it. Bulldozers capable of handling it on Earth need to function here in extreme cold, in abrasive dust, without a mechanic who can be called in from outside. A drill that seizes in almost concrete-like ground 100 meters down is not a setback. It is a loss of water supply. And then there is what happens after the ice comes up. Extraction is the beginning of the industrial process, not the end of it. Ice extracted from the ground must be melted. Melting requires energy. The resulting water must be purified. Martian water carries dissolved salts, perchlorates from the soil chemistry described much earlier in this account, and other contaminants that vary by location. Filtration is required. Chemical treatment is required. More energy. Water on Mars does not come from a tap. It emerges from a sequence of industrial operations that must run continuously, without interruption, because the alternative is running out. But the answer is stranger than expected. Recycling does not solve this. It reduces the ongoing demand, but it does not eliminate it. Even at an optimistic recycling efficiency of 95%, meaning the life support system recovers 95 cents of every dollar of water that passes through it, the remaining 5% is lost continuously. Lost as vapor that escapes through imperfect seals. Lost through plant transpiration in the agricultural module. Lost in human waste processing. 5% per cycle sounds manageable until the math runs long. Every day the colony operates, a fraction of its water supply disappears. Every day, the ice mining operation must replace what was lost. There is no point at which the operation can pause. Mining never stops. But the extraction burden is only part of the picture. The same water that keeps the colonists alive also keeps them shielded. Hydrogen is one of the most effective materials known for absorbing energetic particles. Its low atomic mass means that incoming radiation collides with hydrogen atoms and transfers energy efficiently, slowing particles before they reach living tissue. Water is dense with hydrogen. 1 hydrogen for every oxygen in the molecule, 2 per oxygen to be precise, and liquid water packs those hydrogen atoms tightly enough to matter. Many of the habitat designs proposed for Mars use this property deliberately. Water tanks are positioned around the sleeping quarters, around the most used areas, serving 2 purposes simultaneously: storing the colony's water supply and absorbing radiation that would otherwise pass through the walls. The water is both the drink and the shield. The consequence of that double role is the reveal that this architecture quietly contains. If the water storage fails, 2 systems fail at once. Not one. Not the storage tank that leaked, and the separate shielding system that compensated. Both. The drinking supply drops and the radiation protection drops with it, at the same moment, through the same failure. A crack in a tank, a valve that does not seal, a slow, undetected leak over days, collapses both simultaneously. The colonists would face thirst and elevated radiation exposure in the same emergency. There is no buffer system between those 2 consequences, because the 2 systems are the same system. Site selection cannot escape this geometry. Every candidate location for a Mars base involves a compromise that cannot be fully resolved. A site near the equator offers warmer temperatures and steadier sunlight, but equatorial regions have less accessible ice. Closer to the poles, ice is more abundant, but sunlight is scarcer, and temperatures more extreme. Olympus Mons, at 21 kilometers above the surrounding plains, is effectively above what passes for an atmosphere on Mars. Landing near it would mean operating with even less atmospheric pressure than the Martian average, which is already nearly nothing. The base needs low elevation, which provides slightly higher atmospheric pressure and marginally more protection. It needs flat terrain for landing and construction. It needs proximity to ice. It needs access to scientifically interesting geology, because the science mission is the reason for going. No single location satisfies all of those conditions simultaneously. The named candidate sites reflect these tensions. Jezero Crater, where Perseverance is operating now, was chosen because it is an ancient lakebed. Scientifically rich, geologically accessible, at a latitude and elevation that makes landing viable. Oxia Planum, the target for the European Space Agency's Rosalind Franklin rover, was selected for similar reasons. Both are compromises. Both leave some conditions unmet. And whichever site a crewed mission eventually chooses, that choice becomes nearly permanent. A Mars base is not a campsite that can be packed up and moved when a better location is found. Relocating would mean rebuilding from scratch, abandoning infrastructure that took years and enormous energy to establish. The first base goes where it goes, and the colonists work within whatever that location provides. Water is the master resource. It is not a solved problem waiting to be managed. It is an industrial siege that begins the moment the colony starts operating and never fully ends. The mining, the purification, the recycling, the shielding, all of it running in parallel, all of it necessary at the same time. And the architecture that makes shielding possible is the same architecture that, under failure conditions, takes two systems down together. That double dependency does not appear in the promotional images. It appears in the engineering margins, where the Open Eyes account has to look. But the terms of the choice extend further still. What happens when something breaks? That question sounds simple. On Earth, it has a simple answer. A pump fails, you order a replacement. A circuit board shorts, a technician brings another one. A seal degrades, a new one arrives within days. The supply chain is always there, running quietly in the background, and you never have to think about it because it never stops working. On Mars, the supply chain does not exist. The nearest supplier is not down the road or across the country. It is on another planet, and it can only send anything when the geometry is right. This is the part that sounds abstract until you trace the arithmetic. Earth and Mars orbit the Sun at different speeds. Because of that, the two planets only align favorably for a launch window once every 26 months. Not once a year, not every season, every 26 months. That is when the orbital mechanics make a transfer efficient enough to be practical. Outside of that window, a ship carrying a replacement part cannot simply depart and arrive on a reasonable schedule. The physics will not allow it. And when a window does open, the transit itself takes 6 to 9 months. So here is the arithmetic that colonists would have to live with. A critical component fails. There is no replacement on site. The next launch window is 20 months away. The transit after that window opens is another 7 months. The part arrives roughly 27 months after the failure. Call it 3 years, from break to repair, in the best case. In the worst case, the part was not even scheduled on the next mission, and the wait grows longer. 3 years is not a long time on a geological calendar. On a human one, it is a long time to run a life support system on whatever it has left. The engineering response to this reality is redundancy. Every system critical to survival gets a backup, then a backup for the backup. Life support, power generation, water purification, communications, all of it doubled or tripled. If the primary water pump fails, a secondary pump carries the load. If the primary communications array goes dark, a secondary one can still reach Earth. But the reality is different. Every redundant system has mass, and every kilogram of mass sent to Mars costs an enormous amount to launch. Redundant systems do not travel for free. They displace other equipment. They take up space inside a habitat already built to the absolute minimum. Adding backups solves the failure problem while creating a weight problem, and a volume problem, and a power problem. And then each of those problems needs a solution, which adds more mass. The engineers call this the tyranny of the rocket equation. Every solution costs something, and what it costs is often more of the very resource that is already scarce. So the colony cannot simply bring enough spares. It has to bring the ability to make them. This is where 3D printing enters the picture. The concept is straightforward. Instead of stocking every possible replacement component, bring raw materials and printers capable of manufacturing parts on demand. A pump impeller fails, print a new one. A bracket cracks under thermal stress, print a replacement. The approach is already being tested. NASA has operated 3D printers on the International Space Station, where they have successfully produced basic components. The ISS, unlike Mars, has resupply ships arriving regularly, so printing there is useful, but not existential. On Mars, the ability to fabricate parts would not be convenient. It would be the difference between a functional base and a failing one. But the limitation matters. Printing works for structural parts. Brackets, housings, pressure seals, basic mechanical components, even some tools. Complex mechanical parts machined to tight tolerances in Martian conditions are still at the edge of what current technology can guarantee. And some things cannot be printed at all. Electronics cannot be printed in any meaningful sense. Microchips cannot be printed. Computers cannot be printed. And computers are everywhere in a Mars base. They run the life support monitoring. They manage power distribution. They regulate water recycling chemistry. They process communications. An automated Martian habitat is, at its core, a computer system wearing a habitat around it. Those computers have a specific and expensive requirement. They must be radiation hardened. This goes back to what has already been established about the Martian radiation environment. Cosmic rays reach the surface continuously. These are high-energy particles moving at near light speed, and they carry enough energy to flip individual bits inside a computer's memory. A 0 becomes a 1. A critical value changes by a small amount. If that value is part of a calculation the life support system uses to regulate oxygen concentration, the change is not abstract. Radiation-hardened computers are built with materials and architectures that resist this bit flipping, but that resistance comes at a cost. They are expensive, they are heavy, and they are slow. Not slow compared to the fastest processors built decades ago. Slow compared to what a consumer can buy today at an ordinary electronics store. The radiation hardening process requires manufacturing techniques that lag well behind the commercial frontier. Mission computers running hardware designed to survive deep space have often been compared to running on the equivalent of a decade-old laptop while the commercial world moved on. The processing power is adequate for the tasks designed around it, but it is not adaptable to tasks it was not designed for, and it cannot be upgraded by downloading a software patch from Earth. If those radiation-hardened computers fail, and their backups also fail, the automated systems they manage do not simply continue running at reduced capacity, they stop being automated. The humans inside the habitat must take over, manually monitoring and adjusting every process the computers were handling. Oxygen levels, CO2 scrubbing rates, water chemistry, temperature regulation, power load balancing. All of it, by hand, continuously, with no margin for fatigue or distraction. That is not a theoretical crisis. It is the exact scenario where human error becomes the dominant failure mode. People make mistakes when they are tired, when they are stressed, when they have been managing a crisis for 40 hours without sleep. Automated systems do not. And a base designed around automation, pressed into manual operation by a computer failure that cannot be repaired and cannot be replaced for 3 years, is a base operating at the edge of what its crew can sustain. Failure modes are not limited to the ones engineers anticipated. Martian dust, more abrasive than models predicted, accelerates wear on any moving part that contacts the surface environment. A solar panel junction that developed an electrostatic short from dust accumulation, something already established as a real operating hazard, could take down a power circuit with no warning. Lubricants inside pumps and joints behave differently under the combination of low atmospheric pressure and temperature swings that reach 100 degrees Celsius between a Martian day and night. A pump that would run for years in a controlled environment on Earth may seize in months under Martian conditions, in ways that no accelerated testing on Earth can fully replicate, because there is no chamber on Earth that is exactly Mars. The honest answer is that no one can predict every failure. The redundancy and the printing and the radiation hardening all reduce the probability of any single failure becoming catastrophic, but they cannot eliminate the probability. And on a planet where the repair window is 3 years wide, a low probability event is still an event that will eventually happen. And the supply chain is only one of the constraints that cannot move. The machines are not the only thing that can break. Engineers can model failure rates for pumps and joints and radiation-hardened processors. They can build redundancy into power circuits and water systems and computer banks. What they cannot design around is the person inside the habitat. And on Mars, the person is also a system, one that can fail in ways no redundancy protocol covers. A crew of 6 would carry one trained medic, not a surgeon, not a cardiologist, not a neurologist, not an oncologist. One person with broad emergency training, a medical bay smaller than a standard clinic examination room, and a supply inventory that cannot be replenished for years. That profile works for most things. It does not work for all of them. Consider appendicitis. On Earth, appendicitis is a solved problem. You go to a hospital. A surgeon performs a routine procedure. You go home. On Mars, the same condition requires performing an appendectomy in a confined medical bay with limited instruments, no specialist on the other end of a live consultation, and a communication delay measured in minutes, not seconds. If hemorrhage occurs during surgery, the response options are limited. If infection sets in afterward, the antibiotics are finite, and the pharmaceutical resupply window is measured in years. If the patient goes into shock, the medic is working alone. What is routine on Earth becomes a life-threatening event simply because of where it happens. Fractures carry their own complications. Bones healing in 38% of Earth's gravity may heal differently than they do at full gravity. Setting them correctly matters, and the equipment to do it must be right from the start because complications that would be managed by orthopedic follow-up on Earth have no equivalent escalation path on Mars. The medical bay is the ceiling. There is nothing above it. But here is where it gets stranger than the physical emergencies. The radiation accruing daily in Martian soil, in the air, through the habitat walls, accumulates silently in cellular DNA. Years in, the cancers it generates begin to announce themselves. And when they do, the treatment options are nearly zero. Chemotherapy drugs have limited shelf lives, require refrigeration, and cannot be resupplied on demand. Radiation therapy requires equipment that cannot be transported to Mars. Complex tumor surgery requires a specialist the crew does not have. A cancer diagnosis on Mars does not trigger a treatment course. It triggers a question. Can an emergency return mission be organized in time? And that arithmetic is already in the ledger. The answer is 3 years, in the best case. That is not a treatment path. That is a death sentence with a timeline. The physical emergencies are visible. The psychological ones are quieter, but they carry the same weight. Depression, anxiety, panic attacks, psychotic breaks, all are possible under extreme stress and sustained isolation. The medic carries psychiatric medications, but a crewmate experiencing a suicidal crisis, or one who has become a threat of violence against others, presents a problem that no medication fully addresses. There is nowhere to separate them. No psychiatric facility, no crisis counselor, no hospital. The crew lives in the same pressurized volume, breathes the same recycled air, depends on each other for survival, and cannot leave. The available responses are sedation or physical restraint. Both carry severe ethical costs. Both carry severe practical ones. A sedated crewmate is a crewmate not performing their maintenance duties, not monitoring systems, not contributing to the tasks the group depends on. NASA screens astronauts extensively for psychological resilience. The selection process is among the most rigorous on Earth, but screening measures how a person responds to the conditions they have been in before. Mars is a condition no one has been in before. Nobody truly knows how any given person will respond until they are actually in the situation. The screening reduces the risk. It does not eliminate it. The Mars 500 study tried to measure what isolation does to people over time. 6 volunteers spent 520 days in a sealed mock spacecraft in Moscow, simulating a Mars mission without leaving the ground. The study revealed interpersonal tensions, motivation problems, and disrupted sleep patterns in a group that had been selected specifically for the task. And those 6 people knew at every moment that it was a simulation. They knew they could leave in a real emergency. They knew the desolation outside was a parking lot, not a barren planet. Mars settlers would have none of that psychological cushion. And the conditions on Mars compound the psychological load in ways that are harder to quantify than radiation doses or fracture rates. After weeks, the landscape outside is rust-colored and barren. After months, it is still rust-colored and barren. After years, nothing has changed. No plants, no animals, no weather beyond dust storms, no seasons beyond shifts in temperature and the comings and goings of carbon dioxide ice at the poles. On Earth, even the most extreme environments contain life. Antarctica has penguins and seals. The deep ocean has fish and plankton. There is always something alive, something moving, something that is not geology. Mars is a sterile, static museum of geology. There is no hiking without a sealed suit, no watching clouds, no rain, no birdsong, no smell of grass or salt air or rain on pavement. The sensory world is the interior of the habitat, always, and the view through a window that never changes. Entertainment helps, but here is where the numbers land in an unexpected place. Deep space communication from Mars to Earth operates in kilobits per second. Not megabits, kilobits. At that bandwidth, a single high-definition movie could take days to download. The library of books, films, music, and games that comes with the crew is finite. It was packed before departure and cannot grow at any meaningful rate. Virtual reality has been proposed as a partial answer. A forest walk, a beach, an open sky rendered in a headset. It would help, but the hardware can fail and cannot be easily replaced. And there is a psychological cost specific to the situation that is hard to design around. Knowing the forest is not real, while the actual world outside the window is permanent. Desolation is not the same as choosing to watch a film. The 6 crewmates have the same 6 crewmates, indefinitely. Every story told, every joke already heard, every small personality friction that would be managed on Earth by time apart, by walking away, by spending an evening with different people, has no resolution on Mars. The annoyances that feel minor in the first month are the same annoyances that will still be present in year 3, with no relief. The work itself cannot carry all the psychological weight. Much of Mars maintenance is repetitive. Checking systems, cleaning filters, running diagnostics, monitoring crops, processing waste, recording data. The routine does not change. Wake, exercise, eat, work, exercise. Personal time, sleep, repeat. Meaning arrives in bursts, in genuine scientific discoveries, in data no one has seen before, in the particular satisfaction of a system that holds. But those moments are surrounded by long stretches of ordinary, repetitive labor. ISS astronauts, selected for resilience and rotating home after months, still describe motivation problems on long missions. Mars settlers face years. Some face permanence. Some people find purpose in the larger project, in community, in legacy, in contributing to something that will outlast them. That is real, but it requires a philosophical or spiritual foundation that not everyone can sustain under sustained stress, in the absence of family, in the absence of the world they knew. Hobbies help, but they must be compatible with what Mars actually permits. No pottery kiln, no loud instruments that disrupt a confined crew, no pursuit that requires equipment that breaks and cannot be replaced. The hobbies that survive on Mars are quiet, portable, and low maintenance. The psychological profile the mission requires is not easily found. The person who succeeds needs to be independent enough to function without social support from outside the crew, but collaborative enough to share 3 rooms with 5 people for years. Introspective enough to manage their own emotional state, but socially skilled enough not to become a friction point. Risk-tolerant enough to live with daily danger, but cautious enough not to create it. That is a narrow window, and even people who fit it at departure may not fit it in year 4. The bodies and minds the crew brings to Mars are not just passengers. They are systems. Systems under radiation load, under isolation, under sensory deprivation, under the weight of knowing the nearest help is a 3-year problem away. And the medical bay, the psychiatric medications, and the screening process are all genuine responses to that reality. They reduce the probability of any one breakdown becoming catastrophic. They do not eliminate it. On a timeline long enough, the human systems will be tested just as surely as the mechanical ones. And the human breakdowns are not the final item in the account. The body itself is still part of the equation. The mind adapts or it doesn't. But the physical system has its own timeline, its own drift, its own way of being slowly reshaped by a world it was never designed to inhabit. Human bodies were tuned to Earth, not to Mars. tuned to Earth's gravity, pulling every bone and muscle into a specific kind of work. Earth's magnetic field filtering the worst of what comes from the sun. Earth's 24-hour day setting the rhythm of sleep and hormone release and cell repair. Every one of those parameters is different on Mars. And the question worth asking, the one nobody can fully answer yet, is what happens to a body when you change all of them at once and leave them changed for years? We have a partial answer. The International Space Station has given us years of data on what microgravity does to human physiology. Astronauts on missions of 6 months to a year lose bone density. Their muscles atrophy because the muscles have no resistance to push against. Their hearts weaken because the heart does not need to pump as hard against gravity that is not there. Some develop vision problems, the result of increased pressure inside the skull. Pressure that on Earth drains downward but in weightlessness has nowhere to go. Their immune systems show signs of dysfunction. Most of these effects are at least partially reversible. Return to Earth's gravity, rehabilitate with months of physical therapy, and the body largely comes back. But here's where it gets strange. Mars is not microgravity, it is 38% of Earth's gravity. That partial pull is enough to change the physiology in one direction, not enough to protect it from drifting in the other. And no long-term data on human physiology and partial gravity exists. None. The ISS data is a proxy, a starting point. It is not a map of what Mars does to a person over 3 years, or 5, or 10. Nobody has lived that experiment. Nobody knows what it produces. What we can do is follow the logic chain. Bones maintain their density through mechanical loading. When you walk on Earth, every step compresses bones slightly, and that compression signals the body to maintain density. In 38% gravity, the loading is real but diminished. The signal is weaker. Over time, bone density falls, not as fast as in microgravity perhaps, but continuously. Muscles work the same way. Against lower resistance, they adapt downward. The heart, pumping against a lighter gravitational gradient, grows less robust. These are not dramatic failures. They are quiet adjustments. The body optimizing itself in the relentless way bodies do for the conditions it actually lives in. ISS astronauts exercise 2 to 3 hours per day specifically to fight this drift. Even so, they lose bone and muscle on long missions. Mars settlers would need at least an hour of structured exercise every day, sustained not for a 6-month rotation but for years, in a habitat where floor space is measured carefully and motivation is an ongoing problem. And there is a further complication the ISS data does not capture. Exercise on Mars is less effective than the same exercise on Earth. A treadmill on Earth loads bone because Earth's gravity is pressing a full body weight down through every step. A treadmill on Mars presses less than half that weight through the same step. The mechanical signal to the bone is weaker. Weight vests and resistance harnesses can add load, but they are workarounds, approximations. They mitigate the problem. They do not solve it. Over years of this, some changes become permanent. What alters does not reverse. The skeletal and muscular systems of someone who has lived a decade on Mars may no longer be capable of tolerating Earth's gravity safely. The reverse arithmetic is just as real. Someone adapted to Mars gravity returning to Earth would suddenly weigh 2.5 times what their body had come to expect. Joints, bones, and cardiovascular systems shaped by years of low loading would face a physical environment they could no longer handle. Readaptation, if possible at all, would be measured in months or years of painful, exhausting work. For some colonists, return to Earth after decades on Mars might not be safely possible at any realistic timeline. And that is the situation for adults who arrived on Mars as adults, who developed under Earth conditions before departure. The question becomes harder when you consider children. A child born on Mars would grow in 38% gravity from their first breath. Their bones would develop under that loading, their muscles would calibrate to that resistance, their cardiovascular system would grow into a body shaped by a world that is not Earth. They would be, in a real physiological sense, Martian from the start. Not metaphorically, not as a cultural label. Their bodies would be built for Mars. What happens when that child tries to visit Earth? The honest answer is that nobody knows. But the trajectory of the logic is not comfortable. Earth's gravity, roughly 3 times that of Mars, might be physically dangerous for a body that never experienced it during development. The bones might not be dense enough. The heart might not be strong enough. The joints, calibrated to a lighter world, might be overwhelmed. We do not know, because no child has been born in partial gravity. There is no data, only the physics, pointing in a direction we have not yet had to face. There is another layer still. Radiation on Mars is not only a cancer risk for the individual. Chronic radiation exposure causes DNA damage, and while the body repairs much of that damage, not all repairs are perfect. Errors accumulate. Most are harmless. Some cause cancer in the individual, and some, when they occur in reproductive cells, pass to offspring. Over generations, a Mars-born population would carry an elevated mutation rate compared to an Earth-born population. Some of those mutations would be neutral. Some would increase susceptibility to disease, to cancer, to shortened lifespans. The genetic profile of a Mars colony would begin to diverge from the genetic profile of Earth. Not in one generation, not dramatically, but persistently, over decades, over lifetimes, in a direction that natural selection had not prepared for, and that no one yet understands how to model accurately. The ethical question this raises is not subtle. Adults who choose to go to Mars carry their own risk, but children born on Mars make no such choice. They inherit a body shaped by a world they did not select, carrying an elevated mutation burden they did not consent to, potentially unable to ever safely visit the planet their species called home. The ethics of that are unresolved. They should be unresolved. They deserve more than a paragraph. And the physiological drift the body undergoes on Mars, the slow, quiet reshaping of bones and muscles and hearts and genomes, is not the last dimension of this story. That dimension of the story reaches beyond the body. It reaches into something more immediate, something more practical, and something that, in its own way, is just as irreversible. The question is not only what happens to people who live on Mars, the question is whether they can leave. Getting to Mars requires escaping Earth's gravity, surviving 6 to 9 months of transit, and landing on a world with an atmosphere thin enough to be nearly useless. All of that is understood. What receives less attention is the return. Returning from Mars requires an enormous amount of energy. Scientists call it delta V, the change in velocity needed to break free of Mars's gravity and reach the trajectory home. That energy has to come from somewhere, and there are only two options. Either you bring the return rocket's fuel from Earth, adding enormous mass to an already staggering launch, or you make the fuel on Mars after you arrive. The practical path is the second one. It is called in situ resource utilization, which means using what is already there. The specific process is the Sabatier reaction. It works like this. Mars's atmosphere is about 95% carbon dioxide. You take that carbon dioxide, combine it with hydrogen you have brought from Earth or extracted from Martian ice, and the reaction produces methane and water. The methane becomes rocket propellant. The oxygen, separated from the water, becomes the oxidizer that lets the methane burn. The atmosphere itself becomes the fuel. Carbon dioxide goes in one end, rocket propellant comes out the other. SpaceX's Starship vehicle is designed around exactly this idea. The plan is to land on Mars with empty propellant tanks, set up the fuel manufacturing equipment, and spend months producing enough methane and liquid oxygen to fill the tanks for the return journey. On paper, it closes the loop. The planet provides what the rocket needs, but something is wrong with that plan. Every step of it has to work. Not mostly work. Not work well enough. Every step. The power supply has to run continuously for months. The chemical reaction equipment cannot fail. The atmospheric processing systems have to function in cold, in dust, under radiation, without spare parts that cannot be manufactured on site. The hydrogen feedstock has to be available in sufficient quantity. The tanks have to hold. The fuel has to meet the chemical purity required for ignition. And all of this has to happen over the course of months to years, not days. Any single failure breaks the chain. Not delays it, breaks it. Because the next Earth-Mars launch window opens only every 26 months, and a rescue mission would take another 6 to 9 months to arrive, even after that window opens. A stranded crew is a stranded crew for years, and that assumes anyone could mount a rescue at all. Then there is the launch itself. Launching from Mars is not like launching from Earth. There is no mission control with a full team running simulations and monitoring telemetry in real time. The communication delay between Mars and Earth runs to minutes, not seconds. There are no emergency landing sites. There is no abort to orbit option with a waiting crew. If something goes wrong at the moment of ignition, either the rocket leaves the ground or it does not. Those are the outcomes. No middle option, no recovery scenario, no rescue. Wait, that means the return journey from the moment of landing forward depends on months of flawless industrial chemistry followed by a launch with no backup. Not a modest risk. Not a calculated risk that experience will reduce. A real possibility that the return never happens at all. This is what separates Mars from every frontier humans have crossed before. People draw comparisons to the settlers of the Americas, to the Polynesian voyagers who crossed the Pacific to populate island chains across an entire ocean. Those people faced genuine danger. Many died. The journeys were not safe. But the environments they arrived in were fundamentally compatible with human life. There was air to breathe. There was water to drink without industrial processing. There was food growing from the ground. The planet did not require a working chemical plant to keep the newcomers alive from the first moment of arrival. Mars is not like that. Mars is not a harder version of a known frontier. It is a different category of problem entirely. The comparison flatters the situation. It should not be allowed to stand. So the first settlers may not be pioneers in the familiar sense. They may be permanent residents, not by choice in every case, but because the return option is uncertain enough that it cannot be counted on. Think about what that means in the most concrete terms. It means never seeing Earth again, never breathing unfiltered air outside, never swimming in the ocean, never feeling rain on your face, never standing in a forest, never hearing thunder, never smelling the particular way the air changes after spring rain, that green and wet smell that humans have known for as long as humans have existed. Those experiences are not recoverable. They are not available on Mars. They belong to a world that becomes, over time, a memory and then a blue dot in the sky. And for children born on Mars, even the memory is not available. They grow up in a world of metal and plastic and rock. Earth is a bright point of light in the Martian sky, a place their parents describe, a place that exists in videos and recordings. But as Writing Section 10 established, a body developed entirely in 38% gravity is a body built for Mars, not for Earth. Earth's gravity might not be survivable for them, not safely, not without rehabilitation that may have no endpoint. The blue dot is not just distant, it may be permanently unreachable. Do humans have the right to bring children into a world that confines them this way, with no possibility of departure, under conditions no one chose on their behalf? That question does not have a clean answer. It deserves more than a passing sentence. It will return. But permanence is not only a personal question, it is also a financial one. And the numbers are not forgiving. Apollo sent 12 humans to the surface of the moon between 1969 and 1972. The moon is 3 days away. Missions lasted days to weeks. The total cost was roughly $25 billion in 1973 dollars. Adjusted for today, that is approximately $280 billion. For 12 people, for short stays, on a world 3 light seconds away. Mars is not the moon. Current estimates for a single crewed Mars mission, landing on the surface, staying for months, and returning range from $100 billion to $500 billion. That is for one mission, not a colony, not permanent infrastructure, one round trip. NASA's annual budget runs about $25 billion. The European Space Agency operates on roughly €7 billion per year. Both agencies support dozens of programs. Redirecting enough funding to Mars colonization without cutting everything else would require a scale of political will that has not materialized in any sustained form in the history of space exploration. Private investment is the other argument. SpaceX has promised to make Mars affordable, with reusable rockets driving the cost of transit down towards something accessible to large numbers of people. Elon Musk has spoken of hundreds of thousands, eventually millions, making the journey. Starship is the vehicle intended to do this, but Starship has not yet reached orbit. It has not flown to the moon, it has not flown to Mars. The promises are real promises from serious engineers. The hardware is in development, but development timelines in space exploration have a history. The space shuttle was supposed to fly weekly. It never came close. The International Space Station took far longer and cost far more than projected. Realistic timelines absorb delays measured not in months, but in years and decades. And even if launch costs fall dramatically, the rest of the bill does not disappear. Habitats have to be built, life support systems have to be designed, manufactured, tested, and shipped. Power generation equipment, food production infrastructure, medical supplies, tools, spare parts, communication arrays. None of that cost goes away because the rocket that carries it is reusable. The rocket is one line item. The colony is everything else. Resource extraction from Mars has been proposed as a path toward economic self-sufficiency. Mars has minerals, metals, potentially valuable isotopes. Deuterium, a hydrogen isotope that could be useful for fusion energy if commercial fusion ever arrives, exists in Mars's water. Rare earth elements are present in Martian rock. But rare earth elements exist on Earth too, and mining them on Earth costs a fraction of what it would cost to extract them from Mars, launch them into Martian orbit, and transport them across hundreds of millions of kilometers of space. The economics do not close. Mars cannot pay for itself within any timeline that planning committees can honestly project. The realistic conclusion is that a Mars colony will be subsidized by governments whose political priorities may change, by wealthy benefactors whose interests may shift, or whose finances may collapse. And if the subsidy ends, the colony does not peacefully wind down. A failed colony on Earth could sometimes integrate with local populations, absorb into surrounding cultures, find a way to persist. A failed Mars colony has no surrounding culture, no local population to turn to. A failed Mars colony just dies. SpaceX targets crewed Mars missions in the 2030s. NASA's Moon to Mars program plans crewed orbital missions in the late 2030s, with surface landings in the 2040s. China has announced ambitions for crewed Mars missions by 2045 to 2050. Those are missions, not colonies. True colonization, the kind that involves cities and native-born generations and self-sustaining infrastructure, is a question for the late 21st century at the earliest, and more honestly, a question for the 22nd century, if it happens at all. Some argue that every dollar spent on Mars is a dollar not spent on Earth. Climate change, poverty, biodiversity loss, inequality, these are real problems on the only world humans currently inhabit. Others argue that the technologies developed for Mars, closed-loop life support, efficient food production, advanced recycling, renewable energy systems, carry back value to Earth, and that a multiplanetary humanity is insurance against the kind of catastrophic risk an asteroid, a pandemic, a nuclear exchange that could otherwise end the species entirely. But here is the honest rebuttal to that insurance argument. Even a post-nuclear Earth would still have breathable air. It would still have drinkable water somewhere. It would still have soil capable of growing food. Rebuilding a devastated Earth, however terrible the task, is incomparably easier than maintaining a civilization on Mars under the conditions this script has been describing for the past several sections. Mars is not a backup plan. It is the hardest plan imaginable. And the version of that plan where only the wealthy can afford to leave while most of humanity remains behind raises questions about what, exactly, is being preserved and for whom. The scientific case for going to Mars is real, and it is strong. Mars holds answers to questions about the origin of life, about the history of the solar system, about what planets can become. Exploration is worth doing. But colonization is a different question. A harder question, one that carries the full weight of the physiological risks, the psychological costs, the economic realities, and now the ethical dimensions that have been building across this entire account. The question of who decides and how those decisions get made is the part of the story that has not yet been told. That question of who decides and how those decisions get made is not an abstract one. It lands in the middle of a problem that no space agency, no government, and no private company has yet solved. If people are going to live on Mars together under the same pressures this account has been describing, they need rules. They need a way to settle disputes. They need someone or something authorized to enforce what the rules say. And right now, none of that exists in any usable form. There is a document. The Outer Space Treaty was signed in 1967, and over 100 countries have put their names to it, including every major spacefaring nation on Earth. It says that no country can claim sovereignty over another celestial body. It says that space exploration must benefit all of humankind. It bans weapons of mass destruction beyond Earth's atmosphere, and it holds nations responsible for whatever their space activities produce, whether those activities are government-run or private. These are not trivial commitments. They represented genuine international agreement in a Cold War era when two superpowers were pointing missiles at each other and racing to plant flags on the moon. Then, the pattern breaks. The treaty was designed to stop a war from extending into space. It was not designed to govern a city. It was written for the scenario where nations compete, not for the scenario where individuals from dozens of nations live together in a pressurized habitat on another world, and one of them takes more than their share of the water rations. Think about what that gap actually means. If SpaceX establishes a Mars settlement, is that settlement under United States jurisdiction because SpaceX is an American company? What if the crew includes engineers from Germany, scientists from Japan, physicians from India? What if China establishes its own settlement 50 kilometers away with its own crew under its own rules? Do two legal jurisdictions now exist on Mars? Can they? And if they conflict, who resolves that? The treaty offers no answer. It was not built for these questions. So consider what fills the gap in practice. Imagine a crew of 6 people, months from any contact that could produce meaningful help, arguing over water. Water on Mars is not a comfort resource, it is the master resource, the one that every other system depends on. When 2 people in that crew disagree over allocation and neither will back down, who is the judge? In a 6-person crew, the jury is the crewmates those 2 people sleep beside, eat beside, and depend on for their lives. That is not a jury. That is an impossible social dynamic trying to wear the costume of one. Now carry that further. What happens when the dispute is not about water rations, but about something that, on Earth, would require a court, a prison, a legal system with the physical infrastructure to back it up? There are no prisons on Mars, not even close. Imprisoning one person requires space, resources, guards, and continuous monitoring. In a crew of 6 where every person performs essential duties, removing one person from the operational rotation does not just create inconvenience, it breaks the operation. Execution is ethically fraught and explicitly banned in many of the jurisdictions the settlers came from. Exile sounds like a third option until you examine it honestly. Exile on Mars is not expulsion from a community. Exile on Mars means sending someone outside without a suit, which is immediate death, or with a suit into a terrain with nowhere to go and no support, which is slower death. There is nowhere to send them. There is no adjacent town, no wilderness to disappear into, no civilization within reach. Every option converges on the same outcome. There is a model that has been tried in conditions that carry some resemblance to this. Antarctic research stations operate under agreements that require personnel to abide by established rules and to return home when serious legal issues arise. The Antarctic Treaty Framework has managed disputes at isolated outposts for decades. Scientists at those stations work in extreme cold, in confined quarters, under pressure, far from ordinary life. But Antarctic stations can be evacuated. A medical flight can reach McMurdo Station within hours if conditions allow. A researcher who commits a serious crime or who suffers a breakdown or who becomes a danger to the crew can be removed. The system works because the option to remove someone exists. That option does not exist on Mars. The moment the return window closes, removal is off the table for the next 26 months at minimum. The Antarctic model, which represents humanity's best existing precedent for governance in extreme isolation, fails precisely at the moment Mars would need it most. The alternative is that settlements develop their own governance from scratch, organically, as they go. This is not impossible. Small communities have governed themselves before without importing a legal framework wholesale, but small communities forming their own rules under extreme stress, with no outside oversight and no way for anyone to leave, carry their own dangers. Isolated groups under pressure can accumulate toxicity. Charismatic individuals can accumulate power that outstrips their accountability. Scapegoating provides a psychological release valve that is easy to reach for when everything else is failing. The history of isolated communities on Earth does not inspire uncomplicated confidence. Property compounds this further. The Outer Space Treaty prohibits national territorial claims, but it says remarkably little about individual property or corporate resource extraction. A more recent agreement, the Artemis Accords, tries to address that silence. The Accords, a US-led international framework, establish safety zones around operational sites and affirm the right of entities to extract and use space resources. This moves toward a workable framework for the economics of settlement, China and Russia have not signed the Artemis Accords. They have their own programs, their own timelines, and their own positions on what space law should say. Critics of the Accords argue they effectively privatize space resources in a way that runs against the spirit of the Outer Space Treaty's insistence that space exploration must benefit all of humankind. The disagreement is not merely technical. It reflects a genuine difference in how nations understand whose space belongs to. Competing settlements operating under different legal frameworks, claiming resources using different rules, with no shared court to adjudicate conflicts, is not a stable arrangement. Resource disputes on Earth have triggered wars between nations far better equipped to absorb economic shocks than a Mars settlement operating at survival margins. And while warfare on Mars might seem implausible, because every settlement depends on cooperation, on the shared maintenance of life support systems that could be sabotaged, humans have fought against rational self-interest before. Ideology, nationalism, and grievance have overridden survival calculus throughout recorded history. There is no reason to assume Mars would be different. Then there are the questions that do not yet have categories in existing law. If a child is born on Mars, what is that child's citizenship? Their parents' home nations have not established jurisdiction on Mars. Mars is not a country. It has no government. There is no Martian passport. The child's legal status in any formal sense is undefined. Deeper than citizenship is the question of what that child's life will actually allow. A body that develops in 38% of Earth's gravity from birth may not tolerate Earth gravity safely when grown. We covered what reduced gravity does to bones, to muscles, to the cardiovascular system, and how those adaptations compound over years. For a child whose entire physiological development occurs under Martian conditions, Earth may not be a place they can go. Not as tourists, not as adults choosing to visit the planet their parents came from. Earth could be physically inaccessible to them in the same way that a high-altitude environment is dangerous for someone whose lungs were never built for it. They would be, through no choice of their own, confined. And there is a harder question still. In a settlement operating at the edge of its life support capacity, can reproduction be freely chosen? Or does a community facing real constraints on oxygen, water, food, and space have to regulate when and whether people have children? Reproductive control by committee is among the more uncomfortable phrases in the vocabulary of utopian planning. It describes something that, in most ethical frameworks, constitutes a serious violation of individual autonomy. It also describes something that a resource-constrained Mars settlement might face as a practical necessity, not a theoretical one. If genetic engineering could help settlers tolerate radiation more effectively, or adapt to lower gravity with less physiological cost, does that create an obligation to modify colonists and their children for the environment they will inhabit? Or does engineering humans for specific conditions cross a line that should not be crossed, even in the name of survival? The science of genetic modification is advancing. The ethics of applying it to future generations, who cannot consent, who will be born into conditions they did not choose, is not advancing at the same pace. None of these questions have answers yet. What they have is weight. They accumulate alongside the engineering problems, and the physiological risks, and the economic constraints, and what they reveal is that Mars colonization is not primarily a technical challenge that will be solved when the rockets get good enough and the habitats get robust enough. It is a challenge of reimagining what human society is, what laws mean without enforcement mechanisms, what rights look like when survival depends on cooperation, and what obligations exist toward people who have no voice in decisions that will shape their entire lives. The technical problems are hard. These are harder. And the people who will eventually have to answer them have not yet been born. All of that weight, all of those unanswered questions about law and rights and the children who will inherit decisions they never made, lives inside the civilizational frame. And then you zoom back in. One person. A small spacecraft. The long, slow passage between worlds. Before anyone governs Mars, before anyone argues over water rights or citizenship, they have to get there. That journey takes between 6 and 9 months. 6 to 9 months in a vehicle roughly the size of a large recreational trailer, shared with a handful of other people, with no private space, no silence, no place to go when the proximity becomes unbearable. Every habit becomes visible. Every nervous tick, every snoring pattern, every method of eating, every silence, magnified in enforced intimacy. You cannot leave. There is nowhere to go. In the early weeks, Earth is still large enough to look like Earth. Blue and white, familiar, clearly a world. Then it shrinks. It becomes a bright dot. Then it becomes indistinguishable from Venus, which becomes indistinguishable from the other stars. At some point, a crew member looks out and cannot find Earth at all. Not without instruments, not with bare eyes. This is the moment the overview effect reverses. Astronauts who see Earth from low orbit often describe the experience as profoundly clarifying. The thin fragility of the atmosphere, the artificial nature of borders, the smallness and unity of the planet. That perspective is real. What comes later is different. When Earth disappears into the field of stars, something else moves in. Not perspective, disconnection. A feeling that the place you came from is not just far away, but effectively gone. Psychologists who have studied long-duration spaceflight call it a quiet grief, not dramatic, persistent. Ahead, Mars grows, but slowly. For most of the transit, it is just a reddish dot against the black. No blue, no green, no white clouds, rust and rock, growing incrementally larger over weeks. The crew is traveling toward a place that does not look like a place yet. And during all of it, contact with everyone they love is already broken. Not severed, broken. At its closest, Mars is about 3 light minutes from Earth. A signal takes 3 minutes to arrive. A reply takes 3 more. A simple question and its answer require at least 6 minutes to complete. 6 minutes, if everything moves instantly from the moment of transmission. But Mars and Earth do not stay at closest approach. They drift apart in their orbits. At maximum separation, a signal takes over 20 minutes to cross the distance. A round-trip exchange takes 40 minutes or more. Think about that. You send a message to someone you love. You wait 40 minutes for a reply. That is not a conversation. It is correspondence. It is closer to sending a letter and waiting for one back than anything we associate with the word communication. On the ISS, astronauts can call home with only slight delays, a few seconds at most, a genuine back and forth. On the way to Mars, that is gone. Forever. The crew monitors each other because they have to. Psychological stability is a mission-critical resource. If someone begins to deteriorate, there is no outside help to call in. There is no abort scenario. The spacecraft cannot turn around. A psychological crisis in transit must be handled by the crewmates themselves. With limited psychiatric medications, preloaded counseling protocols, and whatever human support they can offer. The person in crisis is also a friend, a colleague, someone they depend on for their survival. There is no professional distance available. No one knows in advance who will hold up. No test predicts it. The screening processes are thorough. They are not sufficient. Mars 500, a 520-day simulation conducted in Moscow in a sealed mock spacecraft, found interpersonal tensions, motivation problems, and disrupted sleep patterns even among a carefully selected group. And those participants knew it was a simulation. They knew there was a door. The crew approaching Mars has no door. By the time they reach Mars, their bodies have been in reduced gravity for months. Bones have lost density. Muscles have weakened. The cardiovascular system has adapted downward. They arrive at the most physically demanding moment of the entire mission in the worst physical condition of their adult lives. And then, they have to land. Landing on Mars has a name. Engineers call the entry, descent, and landing sequence the 7 minutes of terror. For robotic missions, it has earned that name. Mars has just enough atmosphere to create drag and heat, but not nearly enough to slow a spacecraft to a safe speed. The sequence goes like this. The vehicle enters the atmosphere at thousands of kilometers per hour. The heat shield glows red. G-forces press the crew back into their seats. Parachutes deploy, but cannot finish the job alone because the atmosphere is too thin. Retro rockets fire in the final seconds, burning fuel that was either carried from Earth or manufactured on the surface in advance. Everything is automated. Earth cannot help. The communication delay means that by the time Mission Control receives the telemetry showing the vehicle has entered the atmosphere, the landing has already happened. It is over. The crew is either on the ground or they are not. Robotic landers, with decades of engineering refinement behind them, have historically succeeded roughly half the time. About 50%. That is not a margin. That is a coin. Crewed missions will carry better systems, more redundancy, more engineering attention. But the physics does not change. A heavier payload in a thinner atmosphere with no real-time external help. The crew trusts the vehicle because there is nothing else to trust. And then, if the vehicle lands intact, if the heat shield held and the rockets fired correctly, and the landing site matches where the pre-positioned supplies were sent months earlier, the work begins immediately. Habitat integrity, life support confirmation, power systems, landing accuracy assessed against where the cargo is. All of this performed by people who have just survived 9 months in a small tube and several minutes of controlled falling, in bodies that have lost meaningful bone and muscle, in a state of psychological depletion that no amount of preparation fully prevents. The pre-positioned cargo, sent on earlier unmanned missions, has to be located and checked for damage. Rovers must be unloaded and operated under real Martian conditions that training simulated, but never perfectly replicated. SEALs designed for precise tolerances behave differently after months of Martian thermal cycling. Temperatures swinging roughly 100 degrees between day and night. Connectors jam with dust. Batteries charge below prediction because solar panel efficiency in real Martian conditions does not quite match the models. Nothing is wrong enough to be a crisis. Everything is wrong enough to require troubleshooting. Constant troubleshooting. This is Mars applying what might be called its own version of Murphy's Law, not maliciously, but mechanically. Every system is designed to minimum safety margins because mass is precious and redundancy costs launch capacity. The result is that operations run close to their limits at all times. The brakes work. The stopping distance is minimal, every day. Water is rationed from the first day. No showers, not as a rule, but as a physical constraint. The water budget does not allow it. Wet wipes, dry shampoo, sponge baths, perhaps one shower per week using a few carefully measured liters, every drop captured and recycled back into the system. The habitat smells. Everyone smells. The recycled air carries odors the crew gradually stops noticing because their olfactory systems adapt. Visitors from Earth would notice immediately. The crew cannot. Laundry happens infrequently. Water and energy are too valuable. Socks and underwear are replaced every few days rather than daily. Outer clothing is worn for weeks. The health implications accumulate quietly. Skin infections, fungal infections, treatable with the antibiotics and antifungals in the medical inventory, though some resistant strains require medications the supply may not include. EVA suits require adult diapers for longer excursions. A full EVA runs 6 to 8 hours. That means 6 to 8 hours effectively sitting in waste. Uncomfortable, causing skin irritation, quietly demoralizing in a way that does not make mission briefings, but that shapes the texture of daily life more than almost anything else. Habitat toilets function, but not comfortably. Low gravity and low pressure require airflow mechanisms rather than conventional plumbing. The ISS has documented toilet failures as serious operational events. Mars has no maintenance crew to call. Food begins as pre-packaged Earth rations. Freeze-dried meals, canned goods, shelf-stable items, nutritionally adequate, monotonous in a way that astronauts on long missions consistently report as deeply corrosive to morale. The craving for fresh food is not a preference. It is physiological. Taste, texture, variety. The body wants it and the mind amplifies the wanting. Greenhouses and growth chambers must be established quickly. Plants require light, supplemented with LED arrays when Martian sunlight is insufficient, water drawn from mined and purified ice, nutrients from processed regolith and composted organic waste, and careful temperature and humidity control. Plants are sensitive systems. The wrong temperature kills them. The wrong humidity invites fungal infections or dehydrates the crop. The wrong nutrient balance stunts growth or triggers disease. On Mars, there is no room for failure and no store to visit when failure happens anyway. Lettuce grows in roughly a month. Tomatoes take 2 to 3 months. Wheat and potatoes take 3 to 4 months each. Potatoes are considered a staple candidate because they are calorie-dense and relatively hardy. 3 to 4 months of careful maintenance, water allocation, light management, and nutrient balance for a single harvest. A mid-cycle failure loses all of that. Time, water, energy, and the calories the crew was counting on. Pests arrive even through careful sterilization. Aphids and fungal spores are nearly impossible to fully exclude. In a closed environment with no natural predators, a small infestation can devastate an entire growth chamber in days. On Earth, A failed crop is a financial loss. On Mars, it is a survival calculation. The math is unforgiving. If food reserves stand at 30 days and the next harvest is 60 days away, the colony is already in crisis. Rationing cuts caloric intake, weight loss follows, physical weakness follows that, illness rates rise, and then, in a group of people already under maximum stress in an isolated habitat, conflicts begin over how to distribute what remains. Equal shares regardless of work output, or allocation tied to labor contribution. There is no neutral answer. Both choices carry costs. Both choices generate conflict. Both choices reveal what a community is actually made of under pressure. Some missions may bring animals, chickens for eggs, and eventually meat. Fish in aquaponic systems that cycle nutrients through water. Insects, crickets specifically, as a protein source that requires minimal space and generates minimal waste. Each addition adds management complexity and resource demands. Each addition also provides something harder to quantify, something alive to tend, something that responds, a small but real form of connection in an environment otherwise defined by inert machinery and recycled air. The goal, years into the settlement, is food independence, no longer dependent on Earth resupply for survival. That independence takes years to establish and never becomes permanent. One greenhouse pressure loss, one power failure, one water contamination event, and the colony is back to rationed bars and diminishing reserves, starting the agricultural clock over from the beginning. This is the arrived life, not the mission as imagined in briefing rooms and promotional materials. The weekly shower, the 40-minute wait for a reply to a message sent to someone you love, the potato harvest, 3 months away, that everything depends on, the daily radiation reading that is never safe, only familiar, the 6 crewmates who are, by now, your entire world, in every sense of that word. Whether any particular person can endure all of it, the transit, the landing, the years of minimum margin daily life, remains genuinely unknown. No screening process has identified the trait, no simulation has replicated the conditions. The only test is the thing itself,